Welcome back to our channel. Before we start, tell us, where are you watching this video from? We love connecting with all of you around the world. Today, we're diving into the fascinating world of aviation. Have you ever wondered how humans went from floating in hot air balloons in the 18th century to flying in modern jets that can cross continents in just a few hours? In this video, we'll explore the history of aviation, the milestones that shaped flight, and the science that makes it all possible. Whether you're a student, an aviation enthusiast, or just curious about how airplanes work, this video is packed with interesting facts to take your knowledge to new heights. Aviation is the science, technology, and practice of flying aircraft. It encompasses a wide spectrum of human achievement, from the early attempts at gliding and balloon flight to modern commercial aviation, military operations, and spaceflight. The field of aviation integrates principles from physics, engineering, meteorology, and navigation, creating a multidisciplinary domain critical to global transportation, commerce, and defense. Aviation can be divided into several categories, including civil aviation, which involves passenger and cargo transport; military aviation, focusing on defense and strategic operations; general aviation, encompassing private, recreational, and instructional flying; and unmanned aerial systems, which are increasingly significant in modern logistics, surveillance, and research. Historical development of aviation. The development of aviation can be traced through several key stages. Early human attempts at flight involved kites, gliders, and balloons. In the late 18th century, the Montgolfier brothers successfully launched the first manned hot air balloon, demonstrating the principle of lighter-than-air flight. The 19th century saw significant experimentation with gliders and powered flight concepts, including designs by pioneers such as Sir George Cayley, Otto Lilienthal, and Samuel Langley. The breakthrough in controlled, sustained-powered flight came with the Wright brothers in 1903. Their Flyer aircraft utilized a combination of lift, propulsion, and control surfaces to achieve sustained flight. This achievement marked the beginning of modern aviation. During World War I, rapid advancements occurred in aircraft design, propulsion, and armaments, as nations recognized the strategic value of air superiority. By World War II, aviation had matured significantly, incorporating all-metal airframes, powerful engines, advanced aerodynamics, and long-range bombers and fighters. Post-World War II, aviation focused on commercial air transport expansion and technological innovation. Jet engines revolutionized air travel by enabling higher speeds, longer distances, and more efficient operations. The Cold War era drove further advancements in military aviation, including supersonic aircraft, stealth technology, and precision-guided weapons. Simultaneously, civil aviation expanded globally, with airliners connecting continents and contributing to globalization. The operation of aircraft relies on four fundamental aerodynamic forces: lift, weight, thrust, and drag. Lift is the upward force that counteracts the aircraft's weight and allows it to ascend. Lift is generated primarily by the wings, which are shaped to create a pressure difference between the upper and lower surfaces through the principle of Bernoulli's theorem and airfoil design. Weight is the gravitational force acting on the aircraft. It includes the weight of the aircraft itself, fuel, passengers, cargo, and any additional equipment. Maintaining an appropriate balance between lift and weight is essential for stable flight. Thrust is the forward force produced by the aircraft's engines. In propeller-driven aircraft, thrust is generated through the rotation of propellers, while in jet-powered aircraft, thrust results from the expulsion of high-speed exhaust gases. Thrust must overcome drag, the aerodynamic resistance of air acting opposite to the aircraft's motion. Drag is divided into two main types: parasite drag, caused by friction and shape resistance, and induced drag associated with the production of lift. Efficient aircraft design seeks to minimize drag, while maximizing lift and thrust performance. Aircraft design is a highly specialized field integrating aerodynamics, materials science, propulsion, and systems engineering. The primary components of an aircraft include the fuselage, wings, empennage, tail, landing gear, and propulsion system. Fuselage. The fuselage is the central body of the aircraft, providing structural support and housing for passengers. Cargo, avionics, and flight systems. It is designed to withstand aerodynamic forces, pressurization, and landing stresses while maintaining minimal weight. Wings. The wings generate, lift, and are designed with specific airfoil shapes to optimize airflow. Wing design varies depending on aircraft type and mission profile. For instance, commercial airliners utilize high aspect ratio wings for fuel efficiency and stability, while fighter jets employ swept or delta wings for high-speed maneuverability. Empennage. The empennage, comprising the horizontal and vertical stabilizers, provides stability and control in pitch and yaw. The horizontal stabilizer maintains longitudinal stability, while the vertical stabilizer prevents unwanted side-to-side movement. Landing gear. Landing gear systems allow for safe ground operations during takeoff, landing, and taxiing. Modern aircraft often use retractable landing gear to reduce drag during flight. Propulsion system. The propulsion system supplies thrust for flight. Commercial airliners primarily use turbofan engines, which combine high bypass ratios for fuel efficiency with sufficient thrust for takeoff. Smaller aircraft may use piston engines or turboprop engines, while military aircraft and supersonic designs frequently employ turbojets or afterburning turbofans. Aircraft. Structural integrity relies on lightweight but strong materials, such as aluminum alloys, titanium, and composite materials. Composite materials, including carbon fiber and fiberglass, are increasingly used in modern aircraft for their high strength-to-weight ratio, corrosion resistance, and ability to reduce overall weight. Flight instruments and avionics. Aviation safety and navigation depend heavily on flight instruments and avionics systems. Basic flight instruments provide essential information on altitude, airspeed, attitude, heading, and vertical speed. These include the altimeter, airspeed indicator, attitude indicator, vertical speed indicator, and heading indicator. Modern aircraft employ advanced avionics systems for navigation, communication, and flight management. Global Navigation Satellite Systems, GNSS, such as GPS, allow precise positioning and route planning. Flight Management Systems, FMS, integrate navigation, performance, and autopilot functions to optimize flight efficiency and reduce pilot workload. Radar and Traffic Collision Avoidance Systems, TCAS, enhance situational awareness and prevent mid-air collisions. Autopilot systems have evolved to handle complex flight tasks, including takeoff, climb, cruise, descent, and landing. While pilots remain responsible for overall flight safety, automation reduces fatigue and enhances operational efficiency. Particularly on long-haul flights, aerodynamic efficiency is critical to flight performance, fuel economy, and environmental impact. Factors affecting performance include wing design, fuselage shape, control surfaces, engine power, and environmental conditions such as air density, temperature, and wind. Aircraft operate within specific performance envelopes, including maximum takeoff weight, climb rate, cruising speed, and landing distance. Engineers and pilots must account for these limits to ensure safe operations. Performance calculations involve complex interactions between aerodynamics, propulsion, and atmospheric conditions. High-performance aircraft, including fighter jets and aerobatic planes, utilize specialized designs for maneuverability, speed, and structural integrity. Commercial airliners prioritize stability, passenger comfort, fuel efficiency, and noise reduction. These differing requirements drive diverse design, philosophies, and technological approaches in aviation. How airplanes take off, climb into the sky, and cruise at high altitudes. We'll break down the science, the steps pilots follow, and the technology that makes it all possible. Takeoff is one of the most critical phases of flight. It begins with the aircraft on the runway, fully prepared for departure. Before takeoff, pilots complete thorough pre-flight checks, ensuring all systems, engines, and instruments are functioning correctly. Air traffic control provides clearance, confirming that the runway is clear and weather conditions are safe. The takeoff itself involves accelerating the aircraft to a speed called V1, the decision speed. Below V1, a pilot can safely abort the takeoff if necessary. Once V1 is reached, the aircraft must continue the takeoff even if an emergency occurs. Shortly after the aircraft reaches VR, the rotation speed at which the pilot gently lifts the nose wheel off the runway. Lift generated by the wings increases rapidly as speed rises, allowing the plane to leave the ground. Modern aircraft use advanced thrust management systems to optimize engine power during takeoff. Turbofan engines provide immense thrust while maintaining fuel efficiency. Wing flaps are extended to increase lift at lower speeds, while spoilers remain retracted to reduce drag. The coordination of these systems ensures a smooth, safe liftoff, even for the largest commercial jets. After leaving the runway, the aircraft enters the climb phase, gradually gaining altitude and speed. During climb, the aircraft follows a carefully calculated flight path that balances engine performance, fuel efficiency, and air traffic control requirements. Pilots monitor engine instruments, airspeed, and pitch to maintain a safe climb rate. The climb phase is influenced by several factors: aircraft weight, weather conditions, and runway length. Heavier planes climb more slowly, while strong headwinds can reduce climb performance. Modern aircraft are equipped with autopilot, systems that assist in maintaining optimal climb angles and speed, reducing pilot workload and enhancing safety. Climb is divided into stages: initial climb, immediately after takeoff; intermediate climb, where the aircraft transitions to cruising altitude; and final climb, where speed and altitude are stabilized before reaching the cruise phase. Each stage is carefully coordinated with air traffic control to ensure safe separation from other aircraft and compliance with flight corridors. Once the aircraft reaches its cruising altitude, usually between 30,000 and 40,000 feet for commercial jets, it enters the cruise phase. This is the longest phase of flight, where fuel efficiency, speed, and passenger comfort are the main priorities. At cruising altitude, the air is thinner, reducing drag and allowing higher speeds with less fuel consumption. Pilots use flight management systems to adjust throttle settings, monitor engine performance, and optimize the aircraft's trajectory. Modern airliners are equipped with fly-by-wire systems, which electronically control flight surfaces for smoother, more precise handling. Navigation during cruise relies on a combination of satellite-based systems, GPS, ground-based navigation aids, and onboard autopilot. Pilots continuously communicate with air traffic control, ensuring safe separation from other aircraft and adapting to changing weather or traffic conditions. Weather plays a significant role during cruise, as turbulence, storms, or wind patterns can impact comfort and fuel efficiency. Advanced radar and meteorological tools help pilots anticipate and avoid adverse conditions. Fuel management is critical during the cruise phase. Airlines calculate fuel consumption carefully, accounting for weight, distance, altitude, and expected winds. Modern aircraft are designed for long-range efficiency, with winglets, optimized aerodynamics, and high-bypass turbofan engines that reduce fuel burn and emissions. Passenger experience during cruise is influenced by cabin pressurization and environmental control systems. At high altitudes, the air outside is too thin for humans to breathe, so cabins are pressurized to maintain comfortable oxygen levels. Temperature, humidity, and air circulation are carefully regulated for passenger comfort and safety. Throughout takeoff, climb, and cruise, safety is the top priority. Aircraft are equipped with multiple redundant systems to ensure that any failure can be managed without compromising flight. For example, multiple engines, backup hydraulics, and dual navigation systems provide layers of protection. Modern avionics enhance situational awareness for pilots. Electronic flight instrument systems, EFIS, replace traditional analog gauges, providing real-time data on speed, altitude, attitude, and engine performance. Traffic collision avoidance systems, TCAS, alert pilots to potential mid-air conflicts, while automated alerts monitor weather and flight path deviations. Aircraft performance data, including climb rates, speeds, and optimal altitudes, are pre-programmed into flight management systems. Pilots follow these guidelines closely but are trained to respond manually. In case of unexpected situations, even during the smoothest flight, countless invisible forces interact with the aircraft. Jet streams, pockets of rising air, shear winds, and temperature boundaries all shape the experience. Engineers built aircraft to withstand these shifts without passengers ever noticing. The wings flex gently, responding to atmospheric movements. Engine nacelles adjust airflow with millimeter precision. Stabilizers compensate for subtle drifts, keeping the aircraft aligned with its route. Through all this, the aircraft remains steady, a result of decades of aviation evolution. Takeoff, climb, and cruise are the first three major phases of any flight. Each phase requires precise coordination of aerodynamics, engine performance, avionics, and pilot expertise. From the moment the wheels leave the runway to reaching cruising altitude, technology and human skill work together to ensure a safe, efficient, and comfortable journey. Understanding these phases not only reveals the complexity of modern aviation, but also highlights the careful planning, engineering, and decision-making involved in every flight. It demonstrates how aircraft systems, environmental conditions, and human factors interact to achieve optimal performance while maintaining the highest standards of safety and reliability. High above the world, the aircraft continues slicing through the calm, thin air of the upper atmosphere. Hours may have passed in the serenity of cruise, but a flight is never truly still. Every journey must eventually arc downward, returning the machine from the silent highways of the sky to the structured, pulsing world below. Part 3 explores that return, the descent, the approach, and the landing, phases where precision becomes everything. The beginning of descent, leaving the realm of silence. The transition begins long before passengers notice anything. Deep inside the aircraft's systems, calculations start to work backward. Altitude, distance to destination, wind direction, expected traffic, and terrain ahead. A descending aircraft must lose its altitude gracefully, following an invisible, carefully measured slope. Too steep and it becomes inefficient. Too shallow, and it risks conflict with other flight paths. Far ahead on the horizon, the faint curvature of the Earth shifts as the aircraft gradually adjusts its pitch. Engines reduce power. The smooth hum changes tone. The nose lowers just slightly, a subtle tilt signaling the start of descent. Outside the windows, the world slowly reappears. What was once a distant haze begins forming into definable shapes: coastlines, mountains, fields, and cities. The sky, once a deep and endless blue, starts to lighten as thicker layers of atmosphere draw closer. Descent is not a simple downward fall. It is a controlled slide through the sky, managing speed, altitude, pressure, and airflow all at once. Throughout this phase, the aircraft carefully exchanges altitude for efficiency, gliding through layers of wind and temperature shifts that exist like invisible staircases. Weather and the invisible challenges below. Unlike cruise, descent brings the aircraft into more dynamic air. Clouds appear, forming towering shapes of moisture and turbulence. Jet streams fade, replaced by shifting winds that bend and twist. Beneath the aircraft, warmer air rises, creating ripples that vibrate through the wings. Modern aircraft are built to read this environment with extraordinary accuracy. Weather radar scans ahead, painting a detailed map of storms, rain cells, and air movements. Temperature probes respond instantly. Flight computers gently adjust, pitch and thrust to keep the aircraft stable as it drops through. Layers of atmospheric change. No matter how clear the skies look, descent is always a negotiation, a conversation between machine and air, balancing the art of flying with the science of aerodynamics. Approach, entering the most controlled airspace in the world. As the aircraft continues losing altitude, it approaches its destination's airspace, a region of intense coordination, where hundreds of flights may be, arriving and departing in synchronized patterns. This is one of aviation's most precise environments. The aircraft now aligns with a specific arrival route, a long, winding pattern designed to space aircraft evenly and safely. These arrival procedures guide planes around mountains, through traffic flows, and into the exact path needed for landing. Altitude is stepped down in stages. Speed reduces steadily. The world outside becomes more recognizable: buildings, roads, highways, rivers, and coastlines creating a living map. Wings and fuselage feel the growing thickness of the air. With every 1,000 feet descended, aerodynamic forces change. Air density increases, drag rises, and the aircraft's behavior shifts. Systems compensate automatically, adjusting trim and power to keep the descent smooth. Below, the airport slowly comes into view. Though still far away, a cluster of runways, taxiways, lights, and terminals waiting like a distant gateway. Once cleared for final approach, the aircraft begins a critical maneuver, lining up with the runway. The runway itself may be only a thin strip from afar, surrounded by empty fields or city lights, but for pilots and systems, it is the single focal point of the entire mission. The aircraft turns gently, often over lakes, coastlines, fields, or city edges, positioning itself precisely in line with its landing path. The world outside now moves at a slower, more deliberate pace. The aircraft's altitude decreases quickly but smoothly. Speed must be managed with incredible precision too fast. And the landing becomes dangerous. Too slow and lift begins to fade. At this stage, the wings respond more dramatically to changes in airflow. Flaps extend, increasing the wing's surface area and generating additional lift at lower speeds. These flaps change the aircraft's shape, transforming it from a high-speed cruiser into a slow, stable glider ready for touchdown. Landing gear deploys with a distant mechanical movement. Beneath the aircraft, wheels rotate freely, prepared to meet the runway after hours of flight. Drag increases, adding resistance that helps reduce speed. The aircraft settles into its final descent path, a straight, invisible beam of guidance from sky to ground. The runway now grows larger with every passing moment. Lights line its edges, forming a glowing corridor that cuts across the landscape. In strong winds or shifting air, the aircraft makes tiny corrections, subtle tilts, adjustments, and stabilizations that keep it perfectly aligned. As the aircraft nears the runway threshold, its descent rate decreases, but its focus intensifies. Air beneath the wings becomes thick and responsive. Ground effect, a cushion of air, created by proximity, to the runway lifts the aircraft gently, causing it to float momentarily before landing. Then, with precision, the main wheels meet the runway. The first contact is firm yet controlled. Tires spin rapidly, matching the aircraft's high landing speed. A brief shudder passes through the fuselage, a natural moment as thousands of kilograms transfer weight back to the earth. Spoilers rise instantly from the wings, disrupting airflow and helping the aircraft settle fully onto its wheels. Reverse thrust engages, pushing air forward to slow the aircraft more rapidly. The runway hums beneath the tires, vibrations building and fading as speed decreases steadily. Within seconds, the aircraft transforms from a flying machine into a ground vehicle once more. The aircraft now rolls along the runway, slowing to taxi speed. The intense power of landing fades into calm motion. Lights guide the way toward the taxiways. The engines return to a quiet, controlled hum. What began with a burst of thrust hours earlier now ends in this gentle, deliberate glide across pavement. The journey through the skies has completed its arc. It reveals the elegance and complexity of the second half of flight. The descent from serene altitudes, the precision of approach, and the choreography of landing. These phases show that aviation is more than machines and engines. It is a collaboration with the atmosphere, a careful descent through layers of weather, physics, and human coordination. Every landing is the result of decades of innovation, radar systems, aerodynamic design, engine reliability, and the skill of flight crews all working together. From the high silence of 40,000 feet to the moment rubber meets runway, the journey reflects the mastery of modern aviation. The aircraft has touched down, completing its journey through the sky. But its mission is not finished. Landing is only a pause, a quiet interval before the next ascent. Now begins the second life of a flight, the intricate choreography on the ground. This phase is invisible to many, yet it is where precision, coordination, and engineering combine to prepare the aircraft for another journey. After touchdown, the aircraft leaves the runway and enters a carefully marked world of yellow lines and glowing blue edge lights. Taxiing is deliberate, a transition from high-speed flight to slow, controlled ground movement. Engines, once roaring at full power, now run at low thrust, guiding the machine toward its gate. The terminal draws closer, with aircraft parked like enormous metallic birds resting between flights. Ramp crews stand ready. A marshaller holds bright orange paddles, guiding the aircraft inch by inch into a narrow parking spot. This final alignment must be perfect. The aircraft must stop with its nose gear exactly on the centerline marker. The engines spool down, fading into silence. The heat shimmer dissolves. For the first time since takeoff, the aircraft rests motionless. The moment the engines quiet, the ramp transforms. Vehicles move into place like parts of a machine waking from sleep. Wheeled chocks curb the aircraft's movement. Cones surround its perimeter to mark a safety zone. The jet bridge creeps forward, preparing to attach to the front door. Baggage loaders approach both cargo holds. Catering trucks dock near the rear door. Fuel bowsers position themselves beneath the wings. Lavatory service vehicles wait for permission to connect. Every vehicle has a role, and each movement is timed to avoid interference with others. Passengers rarely see this, the synchronized dance beneath their feet that ensures efficiency and safety. Technicians begin their walk-around inspection. Flashlights sweep across tires, wheel hubs, landing gear joints, fuselage panels, sensors, ports, antennas, and hydraulic lines. The aircraft's earlier flight is written across its surface. Dust, heat marks, moisture streaks, subtle wear. Even minor discrepancies matter. Engineers inspect fan blades for damage, check for fluid leaks, confirm brake temperatures, and verify structural integrity. Beneath the aircraft, panels open to expose access points where systems can be reset, checked, and recalibrated. A modern jet is not just a machine. It is a living technical ecosystem. And these technicians are its physicians. They understand the sound of each pump, each click of a relay, each fluctuation in sensor readings. While technicians work, the refueling team begins its task. Fuel is the lifeblood of flight, and the quantity must be exact. Not a drop more than needed, not a drop less. Weight calculations come into play. The aircraft's fuel load affects climb performance, cruise efficiency, and center of gravity balance. Thick hoses connect to fueling ports under the wings. Valves open. Fuel flows rapidly, monitored by gauges and pressure sensors. The wing tanks gradually fill, their internal baffles controlling movement to prevent imbalance during flight. Outside, the scene looks calm. Inside the wings, thousands of liters of jet fuel flow like energy being restored. Inside the cabin, a new team begins its rapid transformation. The cabin, moments ago filled with the exhaustion and relief of landing passengers, now shifts into preparation mode. Cleaning crews work quickly. Seat pockets are emptied and reset. Trash bags fill with cups, wrappers, and papers. Overhead bins are checked. Lavatories are emptied, washed, and restocked. Freshwater tanks are replenished. Catering crews replace carts, trays, beverages, and supplies. The cabin's lighting shifts to a uniform brightness. Air vents resume a steady, controlled airflow, rebalancing the microenvironment inside the fuselage. Within minutes, the cabin returns to its original state. Fresh, organized, ready. Below the cabin, loaders begin the next stage, loading new luggage and cargo. Each container has a designated weight and position. Aircraft balance is crucial. If the center of gravity shifts too far forward or aft, flight stability is affected. Loadmasters produce a weight and balance sheet, mapping the exact distribution of cargo, baggage, crew, and fuel. Every kilogram is accounted for. Containers slide into the belly with a deep mechanical rumble. Locks engage. Cargo doors close, sealing the aircraft's lower deck. With ground operations nearing completion, the aircraft transitions from external power to internal systems. Pilots and technicians run their checklists. Displays flicker to life. Navigation screens, engine panels, communication radios, flight computers. The auxiliary power unit hums in the tail, powering the aircraft's electrical and air systems. Warnings are cleared. Settings are configured for the next route. The aircraft becomes more animated. Lights on the exterior illuminate. Fans rotate, pumps activate. The machine prepares to awaken fully once again. The jet bridge retracts, rolling backward like a curtain opening before a new act. Doors seal. Cargo hatches lock. Fuel caps are inspected one final time. Crew members confirm readiness. The cabin becomes still. Passengers yet to board or just beginning to take their seats. The ground crew remove wheel chocks. A pushback tug connects to the nose gear. The ramp crew steps back, organizing themselves into a safety arc around the aircraft. A thumbs-up gesture signals the start of the final phase. Pushback, the beginning of the next flight. The tug begins to pull the aircraft away from the gate. Slowly, the heavy machine shifts backward. The wings stretch out confidently, untouched by any obstruction. The aircraft rotates to align with the taxiway. As the tug disconnects, the engines begin to start, one then the other. Fans spin faster, glowing at their centers. Exhaust heat shimmers behind the engines, distorting the air. Moments later, the aircraft becomes self-powered. The ground crew waves their final clearance. The aircraft moves forward. Taxiing toward the runway, it will soon leave behind as it climbs into the sky once more. The final chapter of the journey from landing to takeoff. It reveals an unseen world, a world where hundreds of coordinated actions, inspections, refueling procedures, cabin resets, and technical checks ensure safety and efficiency. An aircraft may land, but it never stops working. The moment it reaches the gate, a new countdown begins. The cycle repeats endlessly. Arrival, preparation, departure. This is the fascinating world of aviation. A world where precision, skill, and teamwork transform a restless machine into a vessel ready to defy gravity again.